there any questions about LSTMs or GRUs from Monday? Questions about LSTMs or GRUs from Monday? So what we're going to look at today is more, I guess we'd say, applications of recurrent neural networks. Now, the first thing I want to talk about, I guess, is really independent of recurrent neural networks, and it is more often used, especially when you're dealing with text, and that is embeddings. Okay? And to begin with, I'm going to talk about word embedding. So the idea is we have a word out of some vocabulary, let's say 10,000 words. How do we normally represent that in terms of feeding into a neural network? One-hot encoding. Yeah, I mean, we could feed a single value that's the number from 1 to 10,000. But it is harder for a neural network really to learn from that than it is just to have this very sparse matrix with one in there that says it's this word. The hub of that one-hot encoding. So here we're going to talk about word embeddings. So the one-hot encoding has two flaws. One flaw is it's the big, right? It takes 10,000 values to specify a particular word. So if you're inputting a lot of words, you have a lot of those 10,000 values. And the second problem is there's no real relationship from one word to another word, right? The relationship between sad and unhappy, there is none. It's just one is at one index and one is at another index. So in embedding, we're going to try and learn some idea of relationships between words. So this might be, let's say, 10K vector. So an embedding is going to be multidimensional. Let's use right now 100. So we'll have 100 dimensions for every word. And each value for a dimension is going to be some floating point number. Okay? So we might have, let's say, dog is 1,234. All right, in our 10,000, 1 to 10,000. But in an embedding, it's going to be some vector of 100 values. Let me give you an example. Not using 100, let's use something like 4. And rather than having a neural network learn it, I'm going to actually provide some features that I have just pre-made up. Okay, so let's say we have dog, cat, lion, king, fish. Okay, these are all of random words from our list of words. Okay, and I'm going to be embedding these by providing some features. So I've got some features like barks, purrs, domesticated, royal. Now let's start with that and see if that works. So dog. Let's just use a number, let's say, between 0 and 1. How barkish are dogs? 1.99. Yeah, there are barkless dogs, right? I mean, they do exist. They don't purr. Well, I have a golden retriever who purrs a little bit. They are very domesticated and not really very royal. Cats do not bark. They purr a lot. They're less domesticated than dogs, would you agree? So let's say a 0.9 for domesticated. And royal, they are kind of. They certainly carry themselves with a certain air of royalty. Let's say 0.1. Lions don't bark, they do purr, I understand. They are not very domesticated, and they have some royalness too. Kings, well, with the inbreeding, there is some barking, but never mind. Let's just say 0, 0, not very domesticated, and they're very royal. And fish don't bark, don't purr, they're slightly domesticated, and they're not royal. All right? So, instead of, if this was our embedding that we were using, then we would convert dog from, instead of being 1, 2, 3, 4, what would its vector be? Nick.
Would it be
0.99, 0.01, 1, and 0, right? Every one of these rows is an embedding. And we could have a matrix that converts from a one-hot into a particular embedding vector, right? Basically, this would be such a matrix, assuming the dog was 0 and cat was, assuming dog was 1, 0, 0, 0, 0, and cat was 0, 1, 0, 0, 0, we could just multiply that by this, and we just end up with a right row. It just picks out a row, okay? So there are some existing embeddings. Glove, for example, is a pre-trained embedding. And all I really mean by that is it's got a list of source words, and it's got a matrix. And there's some interesting things you can do with embedding. Because what we've got is this n-dimensional, right? There's 3 dimensions, but let's say we have more. This n-dimensional space of words where there are words that are close together and are close in meaning. So we would expect unhappy and sad to be a lot closer in this n-dimensional space than we would unhappy and lion, because lions are very happy. But anyway, does that make sense? We can also do this interesting vector manipulation. Let me give you an example. Let's say we take a lion and we subtract, I'm going to put one more in here, wolf. I looked it up and wolves do bark. They bark, they howl too, they bark, okay? Not as much as dogs. They don't purr. They are, in fact, not domesticated. Let's make it a 0.01. And they're not royal. So if I take the embedding of lion, okay, which is this vector here, and I subtract from it the embedding of cat, right? So this is just a vector subtraction. And then I add, so let's say we look in 2-dimensional space. Let's say this were somehow projected into 2-dimensional space. So we've got lion here and cat, let's say here. And then somewhere over here we have dog. What I'm saying is, if I look at that vector here, and that vector here, what's there? That is, I take, and I'm not sure I'm doing my vector, or so E lion minus cat plus dog. That is, what if I took a lion, took out what of the lion is a cat, and put in dogness instead? Okay? I end up at this location, basically. That makes sense? Let's just try the numbers. So lion is 0, 0.9, 0.1. Cat is 0, 0.98, 0.9, and 1. So if I subtract those two, I get 0. I get negatives. 0.08, negative 0.9, and 0. And then if I add dog, 0.99, 0.01, 1, and 0, I get 0.99, negative 0.07, 0.1, and 0. What's closest to this vector? Which word? Rory. If we just looked at the difference between this and each of these, the closest this is to wolf, right? It's pretty close in barkness. It's close in purrness. It's relatively close and domesticated, because what do we have here? We have a 0.1 and a 0 here. So this guy is lion minus cat plus dog is approximately E wolf. Does that concept make sense? Yeah.
Well, I think I understand like the particular. I think I missed like what is the goal of doing that? Like,
Well, we can look at similarities. So we can say, for instance, this is actually it can solve SAT problems, right? Remember the SAT problems? A is to B as C is to, and then you have these choices of what D is. That it can do. So Paris is to France as blank is to England, the UK. I'm not sure what the right thing. Let's say England. London. Yeah, Paris is to France as London is to England. So I can. There's a lot of knowledge in these vectors, right? So we have not only words that are similar to each other, are close to each other, but also relationships between words map as well. Okay. The glove pre-trained embedding is trained. This one, of course, is made up. But you can imagine it has its own 100 features that it has decided are useful for coming with words. It probably doesn't have one feature for barks and one feature for purrs and so on, because it had run out of them pretty quickly. But it has what has turned out to be the most useful features in order to categorize words. We'll talk about how these embeddings get trained in a moment. Yeah. Take a question. Does it make sense what an embedding is?
So glove has 100 features, you say?
Glove, actually, there's a variety of different choices. Among others, there's a 100 feature version.
They're all real words, the features? Or like
The
bars?
features are not words. So every column is a learned feature. Every row is a real word from, I don't remember how big it is, 10,000, 50,000, something like that.
So the columns.
Dictionary. So we
The
have
columns
this.
don't translate to words.
The columns do not translate to words. No, we don't, like many things in neural networks, we don't really know what they mean.
Right.
Okay. So an embedding is this multidimensional representation of an entity. Here we're talking about words. Let's look at how we could train such a thing. All right, let's not use recurrent neural networks. Let's just use regular neural networks. So let's say we feed it into our neural network. We're going to give it 6 words. Word 1, word 2, word 3. Word 4, word 5, word 6. And we're going to feed these through an embedding matrix. Okay. This is basically like the glove embedding matrix. We're going to have to learn this, though. Okay, that's the goal, is we're going to be learning this. And a key thing is, it's the same matrix for all these, right? It's the same embedding. We're going to be learning this word and this word and this word and this word and this word. This word all go through the same matrix into our neural network. And really, this is all one big neural network, but I'm pulling aside the embedding layer specially to show you that. So this could be a 10,000, right? This might be a 10,000 by 50 array. 10,000 by 50 array, right? In which case, we're learning 50 features, right? The embedding is, we'd end up with this 50-dimensional value. And we're going to train this on sentences like I went to blank. So this is word 1, word 2, word 3. And then we're going to leave out word 4. Basically, what it's going to have to do is learn what word 4 is. Let's see, blank, and saw Mickey. All right? Word 4, word 5, word 6. So what's going to come out of here is some y hat. And we want it to match whatever this word is. Where did we get this? We're not going to have people going around and creating 6 or 7 word sentences. We're going to just take a huge corpus of words. Sorry, not of random words, of text, and break it apart into 7 word chunks. Right? It might not even be a full sentence. It might just be we have some large document and we take here are the words. Word 1 is you get out blank, it blows past. And we're trying to have it predict of. And then the next thing we might have to do is we might move over one. We'll say, okay, we give it get out of blank blows past your. Okay, so we just break apart our text into these sequences of 7 words long, and every time we blank out the middle word. It's nice because we don't have to pay anyone to label. We just have to write some code and grab a bunch of existing text. Yet we're still going to use supervised learning because basically we are making up our target by alighting a word from our source. Does that make sense? So that's what we'll train. We're going to be training this neural network in conjunction with these embeddings to be able to do this prediction. And what we'll get out of it is learning these embeddings. And if we train it well, it actually does have these properties as well. Not only close words are together, but relationships between words are preserved across different words. You know, A is to B as C is to D. We can use these embeddings, these pre-trained embeddings. We can go download from Glove these embeddings, and we can use them in our textual problems. So for example, if you did the IMDb example, remember that one? Where we fed in this bag of words? Well, what we could have done is actually come up with embeddings for each of the words. And that would provide a lot more information to our neural network, such that I could probably do better. Make sense? Not make sense? Any questions? Is it just for words? Go ahead.
So from an overall, like high-level perspective, embeddings are something that you kind of pre-train in advance that become like a sort of like better data to feed into what
it can be.
Purposes?
So embeddings can be used by pre-training in advance, or they can be just used in terms of your problem. So as an example here, we would want to use, in Keras, this would be an embedding layer. We'd basically have an embedding layer here that would take our 6 words and turn them into 6 one-hots, turn them into 6 vectors of this dimension. Since we have repeated words, we know they're all words and should be treated the same way. And by forcing us to go through this embedding, this shared matrix, we're allowing the network to learn that we're treating these words similarly, right? As opposed to just having 10,001 hot, 10, basically having 10, 20, 30, 40, 50, 60,000 inputs, 6 of which happen to be ones, and it doesn't know the relationship between any of them. Here, at least, we have a relationship between, there's this one chunk of things, a second, a third, a fourth, a fifth, a sixth, that we're actually doing a lot of sort of pre-processing on. But you can certainly learn it in your problem. And often, if you are dealing with words, you want to be using an embedding. In fact, it's not just words. It's really the fact that it's categorical data. Right? If we think of words, we have these numbers between 1 and 10,000, or depending on your dictionary, 50,000 or 100,000. But it's just a number that represents a particular word, but the number itself has no particular meaning. I'll give you another example of something that has no particular meaning. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So let's say this is categorical information, right? It's a number between 1 and 7. There are relationships between some of these, perhaps depending on your problem, but it's not like 7 is 7 times as big as 1. That is not a relevant relationship. As opposed to, let's say, house price, where 70,000 is 7 times as big as 10,000. Right? Let's say we are trying to predict sales from date and store number. Have I mentioned Kaggle? Okay, so this is one, for instance, competition that they had for money, where for some German store chain, they were trying to predict sales. So let's say we have some data, but not a huge amount of data. Okay, if we have a huge amount of data, we can often just feed it into our neural network, and it'll learn all the relationships between them. But if we have a limited amount of data, it's often a good idea to set up your architecture to kind of force it to use the information that we know about the structure of the problem. So for example, let's say we have a date and a store number. Here's what we might do. We might do a little bit of pre-processing, so feature engineering. Let's break the date into year, month, day, and day of week. Okay, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And we've got our store number and we've got our sales. Right, so sales is just some number, which is not categorical. What about store numbers? Are store numbers categorical? So these are categorical. Day of week, categorical. Day, which is the day of the month, also probably categorical. Month, categorical. Year, maybe that's not, right? So for month, you can say, well, maybe like June, July, and August are going to be very similar in terms of our sales. And very different from, let's say, January, December, and February. Year, we might choose to be categorical, or we might leave it alone. But then what we could do is we could have a neural network, and we could feed in, let's say, the store number, and feed that into an embedding, let's say embedding store. Okay? Basically saying, I bet there's some relationships about these stores. Okay? There's some interesting features about these stores. Maybe some stores are open on Sundays and others aren't. Or maybe some stores are located in the middle of the cities and other stores are in the suburbs. Or some stores are in the south of the country as opposed to the north of the country. We'll just make sure to provide enough space here, enough slots for features that it can learn what's useful and what's similar about stores versus what's different about stores. We would do the same thing for each of the other categoricals. We would feed it an embedding for the day of week. We would feed it an embedding for the month, and so on. Feed those all into here. And our y hat would be our predicted sales. Does that make sense? So we're designing our architecture to push the neural network to kind of learn there's relationships between these store numbers, there's relationships between these days of week, and so on. Because otherwise it just goes into this fully connected network, right? And it would have to kind of learn that these values are related, and these values are related, and these values are related, and let's just pull out some features. And if I only have a limited amount of data, it might not be enough for it to learn that. You had a question?
So you're not training the embeddings, you're already trained on the specific things?
So here's what I'm doing here. In this case, in this case, we were training the embeddings based on these inputs. And then we were going to say these embeddings and use them later for other things. Okay? So that's like Glove. This is roughly how Glove was trained. And we got this embedding, and then this is the piece that we're interested in. Here, what we're saying is, we don't care about this for later. And certainly if we have embeddings for day of the week, it might not be very useful. Right? If we're trying to predict prices in Germany, it may be that the relationship between Saturday, Sunday, and Wednesday is much different from what it is here in the US. So this is going to be purpose-built for this problem. And we're going to learn the neural network and the embeddings all together. Right? Because this is really one big neural network. And we learn it all at once.
And like where would you like take embeddings by itself and use it for something else, or is it?
Unlikely we're going to use it for anything else. It is probably only useful for this particular problem.
But then like why is it different than just having it as like one continuous?
Yeah, so let me show you why. So if we would normally do these as one-hots, right? Those categoricals would just be one-hots. So if we had one-hots, then we would have basically, if we look at our x's, right? We'd have our store one-hots. So if we have 100 stores, this would be x1 to x100, right? And then we have the day of week. So that'll be 101 to 107. There'll be 1 1 on in here, there'll be 1 1 on in here, and so on. If we feed this into a fully connected layer, then we're going to have this big matrix, right? So this is a fully connected. So this will be our W sub, what do we call it? W sub 1? Okay, it's going to be a big matrix, right? The neural network could learn, let's say over the first few layers, to find out important information about the store and important information about day of week and so on. And then eventually, as we get maybe to layer 4, then it could start combining those together. Say, oh, I learned some important stuff about stores and days of weeks and other things, and let me combine them together. But we've made it harder because we've got this giant, so for one thing, we have a lot more weights. Okay? Because this is going to be a pretty big matrix. And we haven't provided it any help in knowing we should focus on pulling stuff out just from the store and just from the day of week. Because it's all, as far as it's concerned, it's just got 1,000 different inputs, and it doesn't know any relationship between any of them. So if we have enough data, it should be able to learn it. If we have a limited amount of data, better to be focusing it on the fact that I want you to pull some information about here and some information here and all these other things, right? In general, when you're using categorical information, you'll often want to use an embedding to sort of pre-process that as it comes in. Other questions? All right, so if you've, until about a year ago, the state of the art for dealing with text problems in machine learning was, or deep learning, was to take an embedding, take a pre-trained embedding and make sure that whatever words you were using go through that embedding. Okay, because we have lots of useful information. And then go ahead and do whatever you're going to do with your network. So for example, state of the art for the IMDb sentiment analysis would have been take an RNN, take your IMDb review, feed in your words. So word, let's say I, goes in here. Feed it through an embedding. What embedding are you going to use? We only have a limited number of reviews, so we want to do some transfer learning. So we want to take advantage of, let's say, glove, right? Glove embeddings were trained on lots and lots and lots and lots and lots of sentences, so they're pretty good. So we might put in here a pre-trained glove. Okay? And then feed that into our randomly initialized recurrent neural net and train on y equals 0 or 1, negative review, positive review. Okay? So we're going to gain a lot from that because as the word comes into the neural network after the embedding, it's going to see that crappy and lousy are close, right? Whereas if we had no embedding, it's going to have to independently learn about crappy and learn about lousy. Does that make sense? And we don't want to train our embedding by ourselves because we don't have a lot much data. We'd like to just take advantage of the fact we already have an embedding that knows crappy and lousy will be close in this 50 or 100 dimensional space. Yeah.
So say we don't have a pre-trained embedding and we're training it from scratch. I'm a little confused about how, in like the training process, how the neural net would know to learn, like, that it's supposed to be learning what things are close, what words are close to another word, for example. Like it feels like in the training process it would just update those weights as it would any other weights in the network, and I'm like not convinced about why they would represent like the closeness that we would expect them to, or like the relationship.
If we are training with this problem, where we are training on just positive or negative reviews, it is unclear how well this is going to do in finding out similarity between words. Okay? If we give it enough data, it'll probably be close, but it still should be able to be capturing positive type words and negative type words, almost certainly, right? That's part of what it would pull out of here. Okay. But it's probably not going to learn that dogs and cats are, among all words, fairly close together.
So it makes sense to me that like we have like this like lower dimensional space, kind of like what we talked about with the dogs and cats and barks and purrs example. That like it'd be pretty easy to see that like okay, so lion minus cat plus dog is going to give you something more. But if you're getting into something that's like super incredibly high dimensional, then everything is far away from each other basically because of just super high dimensional space. So how does closeness even like you mentioned like in like because obviously we want this to happen with a lot of words and know a lot of words, so maybe it's like 10,000 space or something like that. then.
No, we're not 10,000 space,
Or-
we're 100 space,
or
100
100,
dimensional
okay.
space, let's
Okay,
say, or
so
50 dimensional space, yeah.
50 dimensional space, then is it still like reasonable to like, okay, so like Wolf was like, okay, we have that negative point out here, which is close enough to Wolf, and it's like, okay, it's
Yeah.
approximately Wolf,
Yeah.
but then what does closeness even mean at that point? Is there even like good relationships that come out of this? Like, is it still logical as you increase the number of words that you have, that you still get things that are like, would you still get that like?
Yes, yes is the answer, you would still get that.
Okay.
And you'd have to use a similar, right, it's not going to be exactly on. It's not like going to be, this is exactly the vector. It's just going to be the closest vector
Okay.
is this among the words in there. Go ahead.
So are the embedding vectors are like the feature vectors coming out of the CNN networks?
The embeddings, these vectors, are the vectors that are coming out of our embedding matrix.
Yeah, so I'm just like making a comparison to the CNN where we're like training the network to like identifying some specific features and then create like a feature vector. Anything. Is that similar to what we're doing here?
I guess it's similar-ish. Similar-ish, yeah. We're going to skip past embeddings in just a second and go on to what's now state-of-the-art in terms of working with text, yes.
Oh, I was going to ask if you could give an example of how the embedding matrix would look for the INDP example.
Well, we would use the glove embedding matrix. So we would go look at the glove. It has a dictionary of words and their order, right? Because we need to know when we have the word dog, what, you know, this movie was a dog, I guess, does that work? Yeah. What index that goes to. So that's important because we can't randomly choose that. And then it'll also tell us how we get to decide of the couple of different glove matrices, basically, what dimensional space do we have? Is it the 50 one? Is it the 100 one? Is it the 300 one? We would decide that. Okay, so we would take a word like dog. We would go look it up in the dictionary. We would find it was 1,234. And then that's what we'd be feeding in as our word here. A one hot 1,234.
And in case we didn't have the glove,
If we don't have the glove, then we would decide how wide do we want to make this. Right? Do we want 50 features? Do we want 20 features? We probably want to have fewer in our case because we don't want that many parameters to train. But we'd still be better off feeding through an embedding matrix than we would directly feeding in our one hot because we're encouraging it find useful features from the words. Is basically what we'd be doing.
So is W and E, like an example, are they just like multiplied together? Because aren't they not the same dimension?
So let's look at W and E in more. They have to be. So W I'm not going to call that W, I'm going to call it X because it was confusing. So let's say X at I is a one hot word. Right? So let's say this is 32 here. Right? The embedding matrix, except we represent these horizontally, not vertically. So this is 32. Right? We'll multiply this by a matrix. How many rows in this matrix for this multiplication to work? 32, right? So it's going to be 32 by how big? How much?
Anything?
Anything. If we're training our own embedding, it can be anything. If we're using a pre-existing embedding, it's however big that is. So maybe it's 50. Right? Now notice what this does. Given that this is a one-hot encoding, all this really does is pull out a row, right? All this says is pull out the 32nd row. So in Keras, for example, the embedding layer doesn't have doesn't actually take this as input. It takes 32 as input. How can this be 32 and this be 32? This distance is 10K. The whole thing is 10K, right? Because it's a vector of length 10K. And it's converting that or compressing it into something of size, dimension 50. So if this is the 32th one at the 32 entry, that basically says find the 32nd row. And so the embedding layer in Keras takes 32 and says go look at the 32nd row. Don't do this big, sparse matrix multiplication where there's just 1, 1. Right? I know it's just going to be a number from 1 to 10,000. I'll just go and pull it out. So that just makes it faster.
So then the RNN has to learn what the abstract columns mean from the embedding?
The RNN is going to be, the error is going to be pushing these columns to generating something useful to the RNN. So the RNN and the embedding are going to be working together to come up with useful representations.
So when we take a pre-trained embedding, do we also want to train the embedding and modify it as well?
That is a good question. So probably like any pre-trained, we want to freeze it to begin with and maybe do some fine-tuning at the end. Okay? But we want to start with it frozen because if the rest of our neural network is random, we're going to be having large losses. And we don't want those losses to change this embedding yet. Right? We want to go ahead and have this RNN basically learn to use the embedding as is, and then maybe tweak it a little bit. Okay, so we've got this embedding. We've got exabytes coming in here. This is going in to our current neural network. And when we trained the glove embedding, whenever the Google folks trained the glove embedding, they were actually doing this based on prediction of words. It turns out there's useful information in this recurrent neural network, as well as here, that could be useful for your situation. Because the recurrent neural network is going to contain information that's not just word specific, but on context. Let me give you an example. Sally went to the store and bought eggs. All right? An embedding can't tell you the right word here. What do we think the word is? She, yeah. This has to come from history, right? Passed down from the fact that we started out with the word salad. So this information is stored in the recurrent neural network. It's the recurrent neural network that knows this should be she and not he or it or something else. Does that make sense? That's where it's stored? Because that's the only place we have this hidden state that gets passed from time step to time step. So there's a lot more context that the recurrent neural net knows about that the embedding doesn't have. So basically, let's define a language model. A language model allows us to predict missing words. and it's trained on predicting missing words. So we just take sentences and we mask out one or more words, and we say to the model that's learning this, predict what those words are. Okay? So this is an example of using the language model. And often it is an RNN prefixed with an embedding. So language models know lots about words and their relationships, and also larger information about how words get put together with other words. So we can use this for transfer learning. Let's see. So for transfer learning, we've seen an example of transfer learning already. Susan, how have we used transfer learning so far in this course?
Can I pass?
Sure. Alan. Morgan?
I feel like the feature extraction with VGG16.
Yeah, we use like VGG16, right? This pre-trained ImageNet CNN, and we basically took a CNN, chopped off the head, and pasted a new head. Right, so we chopped off the part that was trying to classify into 1,000 different categories and pasted on whatever we were interested in. Right? It could be, is this a dog or a cat? So it could be a classification problem. It could be all sorts of other things. For example, maybe what we could do is we could feed in, so we're no longer in a language model here, we could feed in the output of a CNN into a neural net. And we could say, this is not a sequence, right? This is just a large, what would actually the output of CNN be? If we chop off the head of the VGG, what are we left with as output? Yeah, this feature map, right? So this is basically a feature map. We feed that into an RNN, and maybe we say, generate me a description of what is going on in this picture. There's a boy riding a horse, or something like that. Now, if we want to generate there's a boy riding a horse, we don't want to start with an RNN from scratch, because we've got to now learn how to generate good English. We have something that knows about good English. It is our pre-trained language model. So pre-trained for instance, BERT. Glove was trained by Google, BERT's also trained by Google. Okay, so BERT uses not quite RNNs, but something very similar to RNNs, very complex RNNs with a lot of weights, and basically knows about English. Okay. Knows a lot of the rules of English, knows about English words, and so on. They're a pre-trained language model for lots of different languages. So the idea is take this language model and use it whenever you're dealing with language. So for transfer learning, we take a CNN, chop off the head, paste a new head, and then do what we want in that new head. For here, we'll take Bert, let's say, will chop off the y hat part. This is, if we look at it unrolled, we have here y hat 1, y hat 2, and so on. Right? So this is where it's predicting what the missing words are. We don't care about the missing words. So we're going to kind of just strike that. What are we left with? What's of interest here? Oh, it's actually right in here. We have H1, H2, H3. Here we have X1, X2, X3. These are words. Somewhere we've got an embedding in here. I'm not going to show it explicitly, but the language model has that. So what's of interest in here? Like here, with the CNN, we took the last layer, which is this feature map, which kind of represented what the image was, right? At a high level. What here represents what the sentence is?
Hidden state.
The hidden state. Like this hidden state, the last hidden state?
It's that whole distance to that point, right? So we had information in the previous.
Yeah, this would be, if it's a 3-letter sentence, or a 3-word sentence, then I guess it would be this. So this represents everything up to this point. So we could just take the output of the final state and say that kind of represents the sentence. In fact, let's look at that for a moment, and then we'll come back to using this pre-trained model. Let's look at how translating from English to French works. So we're going to, sorry, not French, because I don't know French, but I know some Spanish words. So we're translating from English to Spanish. All right? We're going to have 2 RNNs. So this is a translation problem. We're going to feed in I am hungry. End of sentence. This is what we're going to call the encoder. We're encoding the sentence. And this RNN, this is one RNN, it is encoding English. So it's tuned for English. This is H1 coming out, H2 coming out, H3 coming out, H4 coming out. We're going to take H4 and just say H4 conceptually is that sentence. And now we're going to feed that into a new network, which is the decoder. So this one's English. And we're going to be converting that to Spanish. So we want to generate Spanish given this input based on this incoming hidden state. Now we haven't really got into the particulars of how we generate, but let's get a start on that. So we're going to say start your sentence. And ideally, this would generate some Spanish. It's really going to be generating a probability distribution, and we'll talk about that in a little bit. But for now, let's just say the most likely word is tango. And then we say, okay, given that the first word is tango, what would the next word be? Hambre, which means hunger, right? I have hunger. And then, if we've so far generated tango hambre, what's the next word going to be? And what's the next word be? End. Okay? I am simplifying here and not talking about how we're actually coming up with this word and this word, because it's really probabilities and probabilities here. We will get to that. So this is now the Spanish decoder. And we train this end to end. It's not like we're training this RNN and then training this RNN. Because if we train this RNN and this RNN, who's to say their hidden states match up at all? I mean, we might have the same size, but who says that they have any relationship to one another? So we would have to train this end to end, feeding it in English, and then using these y hats and comparing them against the y's here.
Is there a way to make H4 like a universal language that can be?
Yeah, you could plug in out one and plug in another one. Yeah. No. So it's going to learn the particular weights for this RNN and this RNN all at once and figure out basically what's a good hidden state that works for capturing this information, but also works for maintaining the information such that we could output this information. Where do we get our training data, by the way? Any thoughts?
Subtitles for movies.
Subtitles for movies? Okay, that could be one. For French to English, the best source is the Canadian government, because they're required to do everything in both French and English, and so they can just take this massive trove of documents. Another thing that can be done is just look out on the web. Look for things that have an English and a non-English version. One problem with that, though, that Google ran into is this feedback loop where people were creating non-English versions of things by running them through Google Translate. And then it's, I don't want to learn better Google Translates from my old Google Translate stuff. I want to learn what humans have been doing in the verdict. So I think there was certainly some talk of actually putting little hidden information in the translations so that it can identify, oh yeah, this was a Google Translate translation. All right. So this is an example of using the hidden state to feed into doing something else with that hidden state, or rather the hidden state having captured everything that went on before. So here's the idea with our language model and transfer learning. Okay. We have our trained language model. We basically take out the H sub, so we feed in n x's. And then we take out H sub n. And then we feed that into something else. Okay? We might feed this into a classifier. You know, we might do a couple fully connected layers and then a sigmoid to do sentiment analysis, positive, negative. We might do a couple fully connected layers and then go into, let's say, a softmax of 10, right, if we're trying to predict 10 different categories. Does that make sense? But we're utilizing the smarts of this RNN. Right? And the fact that the RNN probably understands, like if you say, I was not thrilled versus I was thrilled, it probably has to be representing that somewhere in here. That, wow, those mean quite different things. Questions? Yeah. Yes.
So you kind of explain how the image captioning works, is that as easy to explain? Or is it?
It's not that easy to explain. I'm going to try to show you how. I'm going to show you how we can train generation. Okay? In a moment. Yeah.
So it makes sense to me that, maybe this is more of a question for hidden state, the actual like how hidden states work, but it makes sense to me that hidden state's going to have information regarding the context and like and then everything that happened to get into there. So it's, and then obviously it's going to encode that, and then for decoding it's going to rely on that information to get this finished out. But is there any way that like, so getting meaning and getting like words kind of makes sense to me, but is it possible that like, is it going to be able to pick up on like higher level sort of, like if you're given enough hidden state, it's going to be able to pick up on like higher level ideas of like, yes, this is meaning and this is what's happening, but this is also like English that's happening here versus like Spanish. Because it makes sense that like you could probably feed in both of those things and get very similar hidden, like you could feed in tango hambre and I am hungry and get very similar types of hidden states. That's the whole point of this. But
Well, probably. It's not so clear we can just switch the order of these and go from Spanish to English. Yeah, that's not so clear that that necessarily is going to work. Because we're definitely training this to take the English stuff and encode it for the Spanish decoder. And so we really need a Spanish encoder probably.
so with like just Google, when they have like that switch button, like switch between English and Spanish, it's not the same thing as like just flipping this around. It would be a different like ordered matter.
It's probably a different model. A different model. The other thing is, we could pass more information in here than H4. We might want to say, well, we might have lost some information from here, right? Especially if this was a long sentence or a long thing that we're translating. Maybe like it got fairly summarized by the time we get to H4 and we'd like more information. So we could feed in here H1, H2, H3, and H4. That is the entire sequence of hidden states. Because that's certainly more information that this guy could use. And so that's not uncommon, is to pass in not just the last hidden state, but all of the previous hidden states. And in Keras, when you define a recurrent neural net, you can say, do you want it to return just the last, or do you want it to return all of them? Yeah.
When you have to account for your redundancies for returning all of them, how does it do it effectively? By the time you get to H4, you have a lot. There was also an H3 and H2.
These guy would have to learn which of this is useful or not, is what would have to happen. Okay. So it may find, I'm just going to use the last one, because that has almost everything I want, but occasionally I'm going to go to something earlier. I think what I'd like to do now is, so Monday we're going to continue talking about these language models and look at how we actually generate, both how we train this text and how we generate text. Okay, let me just actually give you just a quick preview and then we'll go on to something else. So remember we saw training on Wikipedia? Here's some Shakespeare. Okay, this was trained on Shakespeare, character at a time, right? So we feed in a character and it predicts the next character. We feed in another character, predicts the next character. And this is now taking that model that's been trained and saying, give me some Shakespeare. We haven't talked about exactly how we come up with these. We know we're getting these probabilities of characters. And as we go through and generate characters, it has probabilities of the next character and so on. But notice some interesting things. Like it gets this idea of, oh, I need to have, what is speaker? Lines, whose line it is, and what the lines are. And it's got actual words for the most. All of them look like real words, as far as I can tell. Well, except I'm not quite sure what a news is, N-U-E-S. And then just to give you some other kind of interesting, we saw Wikipedia the other day. So this is fake Wikipedia. So it's like, got appropriate left brackets, open and close and so on. I don't know it is very meaningful though. And sometimes it generates XML, because I guess XML is part of some Wikipedia pages. But actually look at the XML. Page ends with a closing page. Revision ends an open revision. So it's got some good hidden information that it's keeping, which I think is pretty cool. And another one is generating LaTeX. So it basically took a big book and on algebraic stacks and geometry, and then started generating LaTeX from it. And so they had to make a few changes to make it compile, but like this is what it came up with. Yeah, C discussion of sheaves of sets. There was one which I think said like proof left for the reader or something, which I liked. Yeah, so that's pretty cool. As it says, hallucinated algebraic geometry, and it even made a diagrams. So, and this is what it actually generates, right? Begin proof. It looks like LaTeX, right? And then the Linux source code is interesting too, right? So it actually generates Linux source code from all of the Linux kernel code. And so it looks like C. It's, of course, got a comment before the function. It unfortunately doesn't declare its variables all the time. But it like looks like kernel code. And let's see what else I wanted to show you here. Oh, and occasionally it'll generate a new file. And like it has to start with the GNU license. And then it puts in some include files that might be useful, has some defines, right? And then goes on with functions. So it's just, I think it's interesting. Let me pass this out. This is your assignment and your homework. What I want to talk about is Keras and their implementations of LSTMs. So we have looked at so WHH, WXH, and WHY. Right? So we come out with our Y hat sub 1, Y hat sub 2, and so on. And I said basically that this was part of the LSTM or the RNN, is that we have this output, this weight matrix, an activation function, and an output to a Y hat. Not so in Keras. In Keras, that's not here. All it does is create hidden states. Okay? So how you can think of it is kind of more like this. We have H0 coming in. And here, H1 kind of comes out to the right and on top. And eventually, we've got our last guy, I'm going to call it capital T, and we have H sub T. Right, so this is Keras. And the idea is, by default, what Keras will give you is just this last guy. So if you define a layer in Keras, and you say it's an LSTM or a GRU or an RNN, you're going to feed in a sequence of X's. Okay? And it's going to give you an H sub T. What's the size of this H sub T? Anyone?
Vector 1 by however much hidden state you choose.
1 by however many hidden states you choose. So if you choose 100 hidden states, this is 1 by 100. Okay? So you feed in an X, and the X depends on, it's actually two-dimensional feed in X. So x is going to be right, how many things are you feeding in? Because you could be feeding in more than one value here, right? So at time step 1, you have 2 values. At time step 2, you have 2 values. All the way to time step t, you have 2 values. So in that case, we'd have either 2 by t or t by 2, and I don't know which one. Okay, we'd have to look that up. But it's one of those. Does that make sense? So 2 inputs at each time step, t time steps. So that'd be coming in, and then going out, you would have, let's say, a 1 by 50, if you have 50 hidden states. But in Keras, you can also say, I don't just want this guy. I want all of them. All right? So you can choose to get all of them. And this is where you say return sequences when you're initializing. So you'll say, I want all of them. You guys are going to be doing a problem in computing parity. So the x's that we'll be putting in are just binary values, 0 or 1. And your job is to train an LSTM to generate parity. So you feed in 50 zeros and ones, and it comes out with a 0 or a 1. Does that make sense? No?
What's parity?
Parity XOR, exclusive OR. So are there an even number of ones or an odd number of ones?
Is there a limit on number of layers that we use?
We haven't talked about using multiple RNN layers. Basically, you can take an RNN and you could say, let's feed the output of that into another RNN and then have another RNN stacked on that. So you can have higher and higher level information. But you get one. Okay. And actually, hidden states. You get, what would seem like a good number to use for hidden states in your computing XOR? 10? That'd be a number. Here's what I know. 0 would not be enough, so I'm going to go ahead and give you 1. So you get 1 hidden state. Okay. I know it's doable because your homework, different from your assignment, is to by hand construct an LSTM with 1 hidden state that can compute parity. Okay, so you're going to come up basically what the weight values are. So that's an existence proof, and then we'll see whether we can actually train this guy. What you'll find, there's 2 parts to the assignment. Part number 1 is just use a default. We have a sequence of length 50. We're going to get out what its value is, and we're going to then look at the actual value of the parity for this. So it's a 0, 1. We have our y, it has its y hat, and we'll push the loss back. You'll find it's really hard to train. Like, if you can train it, that's great. I want to see it. Okay? And then we're going to make it a little easier and say, instead of training just from the last parity, let's go ahead and get all the h's. Right? So this should be the parity of x1. This should be the parity of x1 to x2. x1, x2, x3, x1, x2, x3, x4, all the way x1, x to xt. So it's every prefix. And so that way, we're going to be, our loss is going to be, how good was this one, how good was this one, how good was this one, and all the way to how good was this one. So it'll be much easier to train because we have all this loss going back. Does that make sense? What you're doing? So you're going to have to just generate a bunch of random 50-bit strings or vectors, calculate the parity using NumPy, and then use that to train an LSTM. Okay?
What's the parity again?
So yeah, let me tell you. Parity, example. So it's the number of ones mod 2 as one definition. Right? So if we've got 3 ones, it's a 1. If we've got 4 ones, it's a 0. If we've got 5 ones, it's a 1. So this is also equal to the XOR of our values. It's the same thing.
But only ones, so zeros can be anything.
All we care for parity is how many ones do we have. And we just, all we want to know is it an odd number or an even number? So odd number of ones or even number of ones. All right. So next week, last week classes, right? Monday, homework is due. There's a quiz. Thursday, assignment is due. And I skipped a day. Wednesday, I'll give you the finals. Any questions? All right, I will be down in the cafe.